Hello, this video is on the basics of sizes or cardinalities, scientific name of finite sets and natural numbers as such. This is already close to the basement of mathematics, to the fundamentals of it. And that is a difficult subject. Usually mathematics is built on the basis of set theory, so basic objects of mathematics are sets and maps between them. So if you look from this point of view, natural numbers become just sizes of sets. If we have a finite set, not defining anything really, I'm just merely collecting the terms and just illustrations for their meaning. So if I have a finite set, then this will stand for the number of elements of X. So that is also called the cardinality of X. And then sets come with natural operations on them, which are mostly framed as axioms in this description of the fundamentals of mathematics. So one of those operations is a union, or rather disjoint union. Of X and Y. So that is a set which has elements of X and elements of Y combined, and then the cardinality is what is usually written as a sum of cardinalities of X and Y, but we could really turn it around and then say that this is the definition of the sum of two natural numbers. We just imagine sets of their sizes and then take the union. And in that way, natural identities, axioms of operations, addition and multiplication, I'm going to talk about multiplication in a second, becomes very easy to illustrate, to argue for. So with the operation of addition, for example, we know of this commutativity property that the sum of two elements doesn't really depend on the order in which we put in the sum. So that illustrating this union, we could take a set X and imagine it as a collection of cells, little boxes. We can arrange them in any way. We can arrange them in a straight line. So we have here the set which is X, and then we perform the union operation, which is basically stacking two boxes together, stacking two arrangements of little boxes together. So we can do it in this way, we could do it in the opposite way, and that will be really seeing that these two sets are naturally identified. There is a bijective map between them, and that says that the number of elements doesn't really depend if we write it this way or that way. So in each way we have a formula writing the number of elements as sum, and so we have this commutativity property of addition. Multiplication can be seen on the level of sets as the operation of product, Cartesian product. By the definition, this is a set with elements being pairs of elements. The first is from X, set X, and the second in the pair is taken from set Y. And then this is usually known as a multiplication principle if we count the number of elements in the product of Cartesian after René Descartes. We have the following answer. It's a product of sizes of ingredients, of factors in the product of sets. And again, illustrating it is easy, so we could imagine, starting with sort of straight lines of boxes, one for X and one for Y. the Cartesian product is visualized by the rectangular arrangement of boxes with the height y boxes and the length x boxes, and that is clearly symmetric if we change the order of x and y. So the overall large box will be kind of easy to identify in between these two cases. Statistically speaking, we have a natural identification of these two sets, natural isomorphism, which turns into the commutativity property for multiplication. Well, back to addition, the addition had another property which is called associativity, and if you look into what it means, it's really taking three sets, say x, y and z, and then putting them together in, say, this straight line arrangement, and then you could do it in two ways. You could first glue together y and z, or you could first put together x and y and then continue with the last one. So just this picture really exhibits the associativity axiom of the addition, and for the multiplication, the associativity, so this is the commutativity as before, and associativity for multiplication will be exemplified by a three-dimensional arrangement where we take three sets and use them as sort of sides of this three-dimensional arrangement of little cubes. So that is a kind of graphical argument in favor of each of those identities, and maybe the last one is the distributivity. Between addition and multiplication on the level of sets, it will be saying the following. So if you take a union of two sets and then you use it as one of the factors in the Cartesian product, then the resulting Cartesian product you can rewrite as the union of two products. And geometrically, if we follow the pattern before, so the union of x and y taken horizontally will be this concatenation of sort of straight line arrangements of little boxes, and then the z will be the vertical coordinates. So here's x, here's y, and here's z. And then this picture cut in two different, interpreted in two different ways, gives two sides of this identification. So the union of x and y is in here, is a straight line, and then the product with z will be this large picture. So that is altogether this answer. And then these two individually are these smaller rectangles, and glued together, according to the union operation, they give the same answer. So that finally turned into cardinalities, into numbers of elements, will give us the formula that the sum of two numbers multiplied by a third is equal to the sum of two products. That's what is called distributivity of addition and multiplication. And yeah, that is it for this little video. So we'll continue with some other calculations in the next one. Stay tuned.